notebook. Let's see, how do we do that? Somewhere over here. Clip. And let's just grab that to start with. Oops, I chopped part of it. Oh well. Okay, so let's see what we can do with this sucker. So we're given this identity right here that we have to play around with. And we want to find the area under the curve. So that's an integral from 0 to pi over 2 of the sine of x, and then we throw a little dx on the end of it. So that's the structure of the definite integral. A picture of this is always a good idea. So the sine starts at 0. It has a complete cycle from 0 to 2 pi. So half a cycle is up to pi. So it must peak at pi over 2. So there's a rough sketch of the sine. And I'm pretty sure we want that area right there. Was there any tips about using right-hand sum? Does anyone remember what's easier, left-hand sum, right-hand sum, midpoint? Right-hand sum's always easier, yeah. So we're going to go with the right hand and hope that relates to one of the answers they let us choose here. So I need to break up the interval from 0 to pi over 2 into n chunks. Let's see. They're using an m here. Maybe we'll use m chunks instead. So we'll say m subpartitions. So setting up a sum is always the same process. First, you decide how many partitions you want. Usually we're going to go with equal size partitions. So if that's the case, we then calculate delta x, the width of each partition. Well, how wide is my total interval here? Yeah, it's pi over 2 minus 0, so pi over 2 is the total width, and we are dividing that by m. So cleaning that up, we get pi over 2m is the width of our interval. So then we have to come up with our x values that we're going to put in there. So the x sub i's, and they always start at the left endpoint. In this case, starting at 0, we add on our delta x over and over again. Okay. So since we're going to the right, the first one will be 1 to the right and then 2 to the right and so on. So we're going to end up with I times our width, pi over 2m, which just cleans up to be I times pi over 2m. Okay, so similar process to before. Now we just have the fun of a pi thrown around in there too. So let's see. For a particular rectangle in here, like that guy right there, what's the width of that rectangle going to be? What is it? What's the width of that rectangle going to be here according to our work so far? Pi over 2m, yeah. So the delta x is always the width of our rectangle. So we have a width of pi over 2m. And how do we find the height of our rectangle? Yeah, plug our x value into the function, right? So this is our x value right there. Our function is the sine of x. So then I'm going to have to multiply this by the sine of I pi over 2m. I pi over 2m. What's the variable at this point when I'm creating my sum? I is the variable. Yeah, we got to keep that in around because there's x's floating around, there's m's or n's floating around. But when we're doing a sum, I is the variable, right? So that is one chunk of area, and we need to add all of those up. So I is going to go from 1 to m. So let's list out a few of those and see what they look like. So new page. Let's see. I'm going to have a pi over 2m and then times the sine of I equals 1. So that's just going to be pi over 2m. And then we move on to when I is 2. So pi over 2m plus, oops, excuse me, times the sine of 2 times that. So 2 pi over 2m. And then they're just going to keep looking like this. Pi over 2m times the sine of 3 pi over 2m. All the way down to the end of the line here, where we'll have pi over 2m times the sine, oops, m's and n's are getting the best of me, of m pi over 2m. So that's if we write it out without the notation. And we got to get this to resemble that formula they gave us. So let's compare the two of them side by side now. So let's see, go back and let's copy that part right there. All right. So now they don't have that crazy 2 pi over 2m hanging out in front of these, but what does every single term have out in front of it? That same thing, right? So we can just factor out the pi over 2m because m is a constant according to the sum. It's just whatever point we're stopping at. All right, so we factor that sucker out. So let's just highlight that. Oops, let's not use that color highlight. Yellow is just more what? More traditional. So we're going to factor these guys out. All right, what else? Now here they have a 1h, a 2h, a 3h, and 4h all the way down to mh. So do we have, what would be acting as the h here inside of the sign? Yeah, so right, here's our 1, there's our 2, there's our 3, all the way up to m. So if we isolate that, then the leftover part is the pi over 2m, pi over 2m, pi over 2m, pi over 2m. So that's the h in this formula. So to use this formula, I have to make that connection. Choose black. So we have a constant we'll pull out, and then here the comparison in the formula is h for us is pi over 2m. So now I can apply their formula, okay? So they claim that this sum right here is equal to that fraction. So now we have to use that fraction where h is pi over 2m. So cleaning that up. Now remember, we're factoring out this pi over 2m also. We have two versions of it hanging around. So I'm going to end up with that factored out pi over 2m times this crazy fraction. So let's see, my numerator is the cosine of h over 2. So what happens if I divide this sucker by 2? What am I going to end up with? Pi over 4m, correct. So I'll get a pi over 4m minus, and this one is going to be a little trickier. Is there much of a difference between h over 2 and 1/2 of h? Oh, let's see, there's extra parentheses there. Let's zoom in on that. Let's get another shot of it. New screen, screen clipping. Just that part right there. All right, so just something to note that didn't catch my attention at first, red, is this set of parentheses right there. So we have m plus 1/2, then times h. Okay. So let's go back here. Fine print is important. So I guess I'm going to have, just write it as I see it, cosine of m plus 1/2 times, oops, extra parentheses, h, which is what, pi over 2m. All divided by twice the sine of pi over 4m. And so given any particular value of m, like maybe 4 partitions or 10 partitions, we just plug in 10 or 4 into this for m, and out pops the value of that area, at least an approximation of it. Could we clean this up a little bit? Yeah, a little bit, but not too much. About the best we could do is distribute that guy right there. So now we have to say which of those options does it best look like. They give us 4 options. So help me discriminate here. Let's blow that up so it's more readable. Oh, we get more readable, then we lose the screen. That's about as big as I get. Okay, so which one? Let's see, we got our cosine of pi over 4n. Oh, they cleaned up that second cosine. So now let's go back and look here. Let's see, so where they multiplied this through here. So that's going to give me a 2. So I have to add these as a fraction. M over 1 would be 2m over 2. So there's going to be a 2m plus 1 there. So which one is that? Oh, there's going to be a difference somewhere. So like look out front here. These have a pi over 4n, pi over 4n, pi over 4n. Ours should be a pi over 2n. Did they factor something out? Oh, they brought that 2 out. Okay, good catch there. Yeah. All right, so is one of these 3. C has, oh, and they switched to n. It's got to be a minus. Yeah, it can't be a plus. What's wrong with this guy? It's a sign of pi over 2n is wrong. Yeah, process of elimination, it is C. Yeah. Yeah, there's no easy way to do that one there. Yeah. Interesting. Okay. And they want us to do anything else. Ooh, they want us to take the limit as n goes to infinity. So delta x goes to 0. Let's see what we get. Interesting. All right. So for us, let's see, I'm going to have to slide that over a little bit. Oops, I didn't want to do that. What just went away? Oh, that's okay. I want Control T. Let's move this over a little bit. Ah, I missed. Try one more time. Oh, I didn't catch that one. Oh, well. All right, so we want to take the limits. Oops, not a pen. Of this whole thing as m gets bigger and bigger. All right, so let's see, what do we have on our side for doing that? As m, let's see. Oh, okay, I think I see something. As m gets big, right, this fraction in here is going to 0, right? What's the cosine of 0? 1, so that's okay. That's an acceptable result. What about over here? What's going to happen to this? Let's see, that one's more complicated. We'll have to pull that out. And then what's happening to the sign as this goes to 0? What's that? The whole thing will be undefined, right? Because this is, the sign will be going to 0 itself, but this guy also is going to 0. So somehow, maybe we have some connection. Oops, did I get my highlighter? Nope. Between this guy up here and that guy right there. So we're gonna have to pull them together for the limit. And then we gotta analyze what this guy is doing over there. So that one's a little tricky right there. So we'll come back to these two in a minute. Let's take on that one right there. So we've got to consider the limit, and we can take the limit across the difference in the quotient if the limits exist, and don't put 0 in the denominator. So we have what? Cosine of parentheses m plus a half times, help me out here, was it pi over 2m? All right, so cleaning that up, we're going to get, if we add these two right here, that's going to give us a 2m plus 1 over 2. And that is being multiplied by pi over 2m. Oops. So we've got ultimately cosine of 2m plus 1 over 4m times pi. Did I get that right? So we get to exercise some limits before. Okay, so what can you tell me about this thing right here? It's going to 1/2, yeah, because the degree of the top is the same as the degree of the bottom, so the leading coefficients take over. So it looks like this thing right here is going to the cosine of pi over 2, because I'll have 1/2 times pi. It's cosine of pi over 2, 0. So this thing is going to 0. All right, so let's see where we're at. With this limit over here, oops, there they are. All right, highlighter, we've got this guy right here is going to 1, right? This guy right here is going to 0. So now it comes down to what's the behavior of these two right there when I pull those together. So let's see if I can remember all that. I think so. New page, new color. I'm tired of writing in red. Is that blue? Yeah. Nope, it's not a highlighter. All right, so now we have the limit. Ah, darn you, blue. The limit as m gets huge of, let's see, in the numerator we had a 1, but we also have our pi over 4m divided by the sine of, now what was that one? I forgot. Pi over 4m. Let's see, did we deal with that 2 yet? This one right here, that's still hanging around too. Yeah. Oh, we brought it out with that one right there. Okay, so we do have that covered. Okay, so it's up there, and here we have a pi over 4m, right? So does anybody remember what that limit does? Does that look familiar? Yeah, there you go. So way back in Calc 1, you guys did a proof using probably the squeeze theorem that as x gets big, no, as x goes to 0, excuse me, that the sine of x over x, because both of these guys go to 0, that's a problem, but it turns out their slopes are similar. It's like L'Hopital's rule is acting here, if you remember that. This limit goes to 1. So the question is, are these related? And the answer is yeah. If we let over 4m, isn't it true as m gets big, x goes to 0 here? Right? So don't we then have a flip of that guy in black right there? So that means this blue thing right here is equivalent to the limit as x goes to 0 of x over the sine of x, which according to this identity right there has to be I did, right? Because we're saying let x equal that right there. So that means this is an x and that's an x. So that's how we get this right here. So what must that limit be equal to according to that middle line? What happens if you flip 1? 1, you get 1. Yes, this has to be 1 according to that. Holy shit, that was hard. Oh, you said 1, I didn't hear you. Wow, that was an exciting problem. Okay, did we discover anything? I think we evaluated all the pieces of that crazy limit. This one won't be on the test, but it is a heck of a lot of fun, you got to admit. All right, so we've got our 1 right here. We've got a 0 right here. And then this quotient right here goes to what? 1. So what's the net result of this insane limit then? 1. Whew, that was hard. Okay. A lot of work for 1. So our tools here, there are limits of sums. Our limits of sum is very challenging to work with. Did you find this easy or hard? Sam is like, oh my gosh, I don't know what to do with that. So the problem is, for most functions, finding the limit of a sum to get the area is wicked, wicked, wicked hard. We need another tool. All right, let's see if we can get a fantastic out of that online homework first. We believe the limit of u is 1. Wow, it was a lot of work for 1. 1's a nice number. Oh, they're gonna ask me another question? Oh, thank goodness. Oh, they are. Oh, that's a different problem in the homework, okay. So let's take a look at the book for a second to figure out where we're at. Let's see, didn't I put the book in my documents, I think. Math 252, calculus. All right, so hopefully you guys found this PDF of the book useful. You have the most of you have the real book, which is a wonderful thing. All right. So in section 3 here, oops, too far, right there. Blow it up. Can I just do Control plus? Yeah, there we go. All right. So there was a bunch of work to demonstrate this area right here, and then this one right here. So at the moment, we only have formulas for the limits of sums if we can simplify it down to just an x or just an I, if it's just a constant, or if we can simplify it down to like an x squared or an I squared in the sum. We just now found a formula only for the sign of hx, basically. Okay, so far we've been working for a little over a week, and we have 4 integration formulas. Okay, and other functions don't get any easier, right? So now it's time for some new tools. The new tool is called the Fundamental Theorem of Calculus. So we're going to jump into section 4 right now. So there's 2 parts to it. We'll do part 1 and then part 2. And where's my tools here? There we go. Okay, so what part 1 says is if you have a continuous function, so f of x is a continuous function, and we've looked at the idea of the definite integral, so we can look at a definite integral on this. So let's put a little sketch to go with it over here. Choose blue. So let's say this is our function f of x there, and we're going to look at it on the interval from a to b, and let's say a is about there and b is about there. And then just for fun, we're going to pick some x value in that interval. And then for some functions f, we're able to actually calculate the value of that area. Okay, but we can always find it by, theoretically, by taking the limit of a bunch of sums. So the definite integral here would be, let's say, the integral from as x goes from a to x. And then since I have an x there, I can't use it down here too. So we throw in what's called a dummy variable. Usually it's t or u dt. And so we can move x along, we could move it back toward A, or we could move x over toward B, and we can find these areas here. So that's what this represents here. So basically what we've built here, this is an area function with f of x as the top boundary for it. So if it's a function, I could name it as a function. So I'm going to give it a name. I'm going to say this function is called a of x. Now, if it's a horizontal line or a sloped line or a parabola, we have formulas for it. If it's a simple sine function, we have a formula for that now that's kind of difficult that we'd rather not have to look at. But here's the cool thing about this right here. Ultimately, this area function is defined by the integral, the definite integral, right? And the definite integral ultimately is equal to the limits. And there's a couple of ways to define it. I'm going to define it as delta x goes to 0 for a sum as, let's see, I guess I need a I or a K. Let's use I goes from 1 to n of delta x times f of x sub I. All right, so we talked about that definition before. We've applied it for a few different functions. But this is a very tedious process here. And this picture will help us develop a different process. So that picture right there is the key. All right, so new page. We have a of x defined to be the definite integral from a to x of f of t dt. And again, the picture of that, I'll throw you over here. That's f, a, b, x. Oops, that was sloppy. And so ultimately in this area here, we're just going to zoom in on a particular rectangle. Let's just zoom in on that rectangle right there. So there's a whole bunch of rectangles that make up this area. Here, I'm going to say the base of that rectangle is h wide. So I'm going to use an h instead of a delta x because it's easier to write. And then the Riemann sum says we can pick any number inside that interval to evaluate. So again, h is that width there. And so we're just going to pick some number in there, and we're going to call it c. So then the area of that rectangle, let's call it delta A, the chunk of area, is equal to h times f of c. Okay, so it's a continuous function. I can pick any c I want in there in that interval. So that's one way to think about it. So another way to think about it is, let's say we were doing a left-hand endpoint. Okay, if we were doing a left-hand endpoint, then another way to define this rectangle would be, say, take the area at c plus h and subtract the area at c. So how does that work? Well, highlighter. The area at c plus h would be all of this area right there, which is more than what I want. This next part here says subtract the area of c. Now remember, c is the left-hand endpoint, so they're saying, well, subtract this area right here. So if I subtract that area, what's left behind? Well, isn't it just my rectangle? Okay, so I have two different ways to define that rectangle's area. I can say it's h times f of c for the right f of c, or I can say it's this difference right there. Okay. Have you seen anything that looks like that before? Where does that come from? Oh, I don't want to think back to Calc 2. It's part of the definition of the derivative, right? Isn't it the numerator? Yeah, so check this out. So I can do the following. I can say, all right, if I were to take that area function evaluated at c plus h minus the area function evaluated at c, and then I divide by h, I've just made a formula for the slope of the secant line between c and c plus h. Even better, if I take the limit of this sucker as h goes to 0, what is that going to give me? The derivative of the area function. It tells me how the area function is changing. Yeah, this is equal to a prime, the derivative of the area function, evaluated at that number c. Now, there's nothing special about that c. That c could be here or there. It could be anywhere in the interval. As long as the function's continuous, it's okay to pick any possible c. Now, it turns out there's another way to look at it, though. Highlighter. This numerator right here, isn't that my change in area, my single rectangle? Can't I also define that single rectangle as h times f of c? Okay. So I also have this fact, that this same system I have written down here is also equal to the limit as h goes to 0 of the numerator here could also be written as h times f of c divided by h. What happens to that h? It divides out. Okay, that leaves only the f of c, right? Do you see any h's inside f of c? So what happens as h goes to 0? Nothing happens. I still get f of c. Oops. Okay, so here's the beautiful thing that it doesn't seem like a big deal at first, but it turns out it is a huge deal. That, and it kind of makes sense, I think, once you start thinking about it. The rate at which the area changes, and so we're talking about the area we're accumulating under that curve right there, the rate at which the area changes is entirely dependent on the top boundary. Doesn't that make sense? If the function is steeper, shouldn't we be getting more area? And if the function is decreasing, we're not getting as much area as we were before. Totally makes sense physically. So people noticed that before. Oh yeah, that totally makes sense. But they didn't make the real connection here, because people were doing calculus for like thousands of years before they finally made this connection here. And this is what's called the Fundamental Theorem of Calculus Part 1. So I'll break it down. I'm going to write it down in a slightly different way. New page. So what we have, oops, pen, black, undo, is that our area function was defined to be the definite integral from a to x of f of t dt. So that's fact number one. Fact number two that we just discovered is that the derivative of the area function is actually equal to the boundary function. That's the fact number two we just discovered by making that little connection about a change in area. Okay. So if I put these two facts together, and this is the kind of mind-blowing part, is that if I take the derivative with respect to x, right, that's what that prime right there means, doesn't it? Of the area function, which is its definition over there. So from a to x of f of t dt. So if we take the derivative of the definite integral, what does it have to equal according to these two equations? It's got to equal f of x, yeah. It's got to equal f of x, right? That's what this second line right there says. even more profound than that, basically you can think of a derivative as a function of its own. It transforms the look of a function, right? It changed x squared into 2x, okay? It's what's called an operator on functions. So it's kind of like these two operators, the idea of the derivative and the definite integral, don't they cancel each other out? They are opposite operations. They're the reverse of each other. That's what all this ultimately leads to. So I'm just going to give an example that we can apply for that. Okay, so this is the fundamental theorem part 1. And then again, it applies to the definite integral. How about, let's let f of x equal the cosine of x. Pretty sure that's the one I want. Yep. So then we could define an area function on this by saying, okay, find the definite integral from some value a up to x of the cosine of t dt. And remember, I have to put a t in here instead of an x because x is already being used up there and I can't use the same variable for two different things. Okay. And the other connection is that if I take the derivative of this area function, I'm going to get the cosine back. So think back to Calc 1. What function did you take the derivative of and the result was the cosine? It was the sine. So what must our area function be equal to here? Yeah, the area function has to be the sine. It's got to be the sine of x. So now what this part 1 tells us is that if we knew a derivative, we can reverse it and we now know a function we can use as the definite integral. Okay. So that's powerful. So all of those, did you guys memorize a lot of derivative formulas? You memorized a lot of derivative formulas, right? So now, instead of having to do limits of sums like that insane one we did at the beginning of class, we can just look back on our experience with derivatives. Anybody's hair on the back of their neck standing up over this? No? Sam, it's not getting to you there? Maybe tomorrow it will. It's like, oh my God, is that really true? It is. It's so true. So the proof I did, I left out a few steps in the proof. There's a couple of technical details, but that's the gist of it. If you really want to see the few other technical details, the book takes about 2 more pages this size to finish the proof. But that's the idea, that the rate of change of the area function has to be the top boundary function here. There's no other way about it. The part 2 is kind of interesting of the fundamental theorem. Let's jump right to that. So part 2 of the fundamental theorem, fundamental, says that if you have any antiderivative, so they say, now I like to use an A for area, they like to use capital F's and little f's, so calculus is case sensitive if you haven't noticed already. So capital F is an antiderivative. Okay. So, and notice I wrote an antiderivative. Okay, because check this out. If I were to take the derivative with respect to x of x squared, what would I get? 2x, yeah. If I were to take the derivative with respect to x of x squared minus 3, what would I get? 2x. So what this tells me is 2x has multiple antiderivatives, right? X squared is one of those antiderivatives, but really isn't it x squared plus any number? plus any constant. Yeah. So that was something we learned back in calculus, that any two functions, if they differ by a constant, will have the same derivative. Okay. And that goes into part of the proof of the fundamental theorem. But what the fundamental theorem says is that f can be any antiderivative, this one or this one, doesn't matter. Then if you integrate, if you find the definite integral as x goes from a to b, now since x isn't one of these endpoints, I can actually use it in here. I can literally say f of x dx. It's a weird thing to get used to, when you can and when you can't. That it's like when we were subtracting areas earlier, you find the area all the way on the right, and then you take away the area all the way on the left, and that gives you the area in between. Okay, like when I subtracted from the area function earlier. But here I can just do it analytically, algebraically, without thinking about areas. All I do is take whatever that antiderivative is, this one or that one, and I just evaluate it at the right endpoint and subtract the evaluation at the left endpoint. Okay, so let's see. Let's go back to that crazy problem we had earlier. Oh, here's a kind of a trick question. What is the derivative with respect to x of the cosine of x? Negative sign. Okay, yeah, cofunctions always have a negative derivative, right? That's how I remember it. The co leads to a negative. So if I were to try and integrate, let's say from 0 to x of the sine of t dt, according to that theorem, I would need an antiderivative for the sine. Well, what's an antiderivative for the sine? It would have to be negative cosine, yeah, because I'm looking at the sine, I have to bring the negative over to the other side. Yeah. So it says take that thing and evaluate it at the right endpoint, or yeah, right endpoint, x, and then take away that thing at the left endpoint. See, what's the sine of 0? Oh shit, right. Thank you. Oh, that's not an eraser. Cosine, negative cosine. Okay, what is, oh, and I put an x there. This should be a what? 0, okay. What's the cosine of 0? 1, all right. And then here I have a negative negative. So that is a positive. So now I have the opposite of the cosine of x plus 1. All right. Have we seen this before? Let's see. Find the area of the curve, sine of x. That's what this problem is right here. Okay. Now here we're going from 0 to pi over 2. Let's see if it matches the answer we got. Okay, so instead of that x, I want a pi over 2 here. So I want to evaluate this when x equals pi over 2. So that means I want my area should be the opposite of the cosine of pi over 2 plus 1. What's the cosine of pi over 2? 0. So the area must be 1. Okay, think about the work we did on multiple pages at the beginning, and then think about that right there. Sigh of relief comes out. Are you going to expect it to do a problem like that first one on the exam? No, that won't be on the exam. Maybe a take-home exam if I was really mean, but I wouldn't do that. But there are so many cool problems to look at. So now we've just opened ourselves up to answer all kinds of questions. But do we have derivative formulas for every kind of function? The answer is no. We're going to find functions for which we don't have derivatives to go back to. And so we're going to have to come up with some other tricks. So over the next couple of days, what we're going to do is we're going to play around with what derivative definitions do we remember? We can use those as antiderivative formulas. They'll look a little different. Like let's try, let's see, the derivative, oops. And you guys looked a little bit at antiderivatives at the end of Calc 1, is that true? Okay, so if we took the derivative with respect to x of x cubed, what do we get? 3x squared. And if we tried to reverse that, what would the integral, and we're going to do what's called, let's see, I'm going to mention what's called the indefinite integral. And so if I don't put any boundaries on it, it's what's called indefinite. And the catch there, let's suppose I put 3x squared dx. Do we know an antiderivative for 3x squared? Yeah, it's x cubed, right? However, I've lost information when I take the derivative. Like, are there other functions that have a derivative of 3x squared? Yeah, 3x squared plus 1, 3x squared plus 2, 3x squared minus pi. So the indefinite derivative, we always adjust by putting a little plus c on the end, because we lost some information when the derivative was taken. Because again, this guy up here is also equal to the derivative with respect to x of x cubed minus pi. Oops. Okay. Derivatives lose information sometimes. So the integral, you have to say, well, I don't really know if there was a constant or not. So we just throw that in there. Okay. That should be a cube, right? Thank you. Okay. Now, usually we want to know something like just a formula for the integral of x squared dx. What about that missing 3? Can I do something to find that? Answer is sure. We'll be out one sec. The trick here is, this is an equation, right? 3 is a constant, so it can come out, and I can divide it over to the other side. Right? So if I divided by 3, so then over on this side, I would get x cubed over 3. Do I know what constant that is? No. So usually in math, we do squirrely things with constants. Like we say, well, 3 is some arbitrary constant. I don't know which one. So isn't c over 3 just still some arbitrary constant? So we just call it c still. I don't know what it was before. I don't know what it is now. So what if I divide it by 3? Doesn't matter. So we let constants absorb some things. You got to be careful with that. It does work here. Right, and what we're going to do is we're going to see a pattern come out. Like, didn't we have a formula for, like, if instead of a 3, what if that was an n? Oops, eraser. What happens on this side here? Nx to the n minus 1. Yeah. So here we bring the power down and drop the power. We're going the other direction, right? So instead of multiplying, what am I doing? I'm dividing. Instead of dropping the power, I am increasing the power. So we can kind of generalize and say if this was x to the n dx, then we would have to increase the power and divide by that new big power. Okay, so that's what we're going to be doing over the next couple of days, taking derivative formulas we knew and see how to turn them into integral formulas. And sometimes we have to be a little tricky to do that. All right, so we are out of time for fun with math today. We still have a few things to tie up in section 4. Do your best on the homework, and we will go over homework questions and possibly start section 5 tomorrow.